Okay, so last time we calculated what the effective spring constant would look like if I put two springs in series with each other under a given mass with a certain load. So now we're going to do parallel, and what I'd like to do is the exact same analysis that we did before. So we're going to take our spring mass systems here, and now what I'm going to do is I'm actually going to add another spring, I'll call that one S2, to my mass. And I'm going to ask the question, what does the momentum principle tell me for this situation? The momentum principle, as we know, delta P equals F net delta T. Of course, this is zero because everything is static, nothing's moving. Well, this is F net. Delta T comes over, multiplies 0. Okay, so now what we observe is that Ks for our springs has stretched half as much. So the stretch is now half the distance. This is an experimental observation, and that's going to be equal to mg. Again, I'm not deriving anything here. I'm giving you the outcome of an experimental measurement. And so Ks, the effective spring constant, is going to look like 2 mg over s. And so for a single spring, it would actually be twice the distance. So Ks, two springs in parallel, is going to look like 2 times Ks for one spring. Now that's a very short and quick determination, but now we're going to actually go through and we're going to derive the mathematical formulas for how to do this in both cases. GoPro stopper. Okay, so now I'd like to just show you for an example of two springs in parallel how you would equate the spring constant of both of those springs into one effective spring constant. So what we're searching for is going to be K effective. And what we have to do first is we have to identify the forces. So let's write down all the forces that are acting on my mass with a free body diagram. This is going to be mg. And to balance that force, we're going to have the sum of F1 plus F2. They're both pulling upward to return the springs back to their equilibrium position. And that means that they have both been stretched to distance s in this process. So, because of our constrained two springs that have stretched s, we can easily write down, because this system isn't moving, that the momentum principle has to look like F net delta T. And if we now say, okay, nothing's moving, this becomes 0, which is just F net delta T. And I can rewrite this as being F net. And so the net forces are going to be 0. And so that's going to mean that we can rewrite the net force as F1 plus F2 plus, vectors, so minus mg equals 0. So then I can write that F1 plus F2 must be equal to mg. But I can rewrite my f's now in terms of what I know about my springs. So both springs have stretched to distance s, and so I can write that k of spring 1 times the total stretch plus k of spring 2 total stretch is equal to mg. And what we find is that this quantity right here is K effective times S. So this becomes K1 plus K2 times S is equal to mg, which means that this quantity is our K effective. So I can write K effective for springs in parallel is just K1 plus K1 plus K2. And this is true for all sets of parallel springs. If I had 1,000 springs in parallel holding up my mass, I would just write that the K effective for that system, because the stretch is the same, is just the sum of all the spring constants of all the springs. For something in series, we saw that, just to revisit that, K effective, 1 over K effective is equal to 1 over K1 plus 1 over K2. So these are two things to keep track of. This is for series. For parallel springs, it's just the sum of the spring constants. For series springs, 1 over the effective spring constant is 1 over the one spring plus 1 over the second spring plus 1 over the third spring, etc., until you've accounted for all the springs.